Hello everyone. Can I share my screen quick? Okay. Okay. Hello again and welcome to Probing the Black Box, Debugging Kubernetes Networking with Basic Tools and Techniques. And my name is Nguyen. I'm currently working as a DevOps engineer at Viettel Network in Vietnam. And today is my pleasure to present to you about very interesting topic, and that is Kubernetes networking. A bit of context why I choose this topic. And so, in the early day of operating Kubernetes, my team encountered an incident related to Kubernetes networking. At that time, we were very confused and didn't know what to do to debug the errors, let alone fix it. Our final solution was to reinstall the entire Kubernetes cluster. And after that, my boss asked me, I thought Kubernetes was a state of the art platform with all that automation and self healing stuff. Why do I feel like it's a black box that I can see inside? So it was from this question that I had the motivation to choose the topic of today's presentation. Uh, so my presentation is divided into 6 parts. First, I will briefly introduce Kubernetes. Next, we will learn about the basic concepts and components of Kubernetes networking. Then we will take a deep dive into the world of Kubernetes networking, explore how it works and common issues that may arise. Next, I will share some debugging techniques for Kubernetes networking and have a small demo example to show you how to apply the techniques in practice. Finally, I will summarize the key points of today's presentation, and we will have a few minutes to answer your question if you have any. Uh, for those who don't know, Kubernetes is a portable, extensible, open source platform for managing containerized workloads and service that facilitates both the declarative configuration and automation. It was created by Google, then donated to Cloud Native Computing Foundation, or CNCF, in 2014. Uh, Kubernetes provide features such as automating application deployment, self-healing, auto-scaling, service discovery, load balancing, and many other features that make deploying and managing application easier and more efficient. But in addition to the benefit that Kubernetes brings, it also brings many challenges, many from its complexity and level of abstraction. Kubernetes has many abstraction layers that hide the specific implementation details, making it difficult for beginners to understand and debug when problems arise. One of the common issues that you may have encountered when working with Kubernetes is networking. And in the next section, we will learn about the basic concepts that make up Kubernetes networking. First, let's talk about container networking in Linux. Network namespace are a way to create virtual network environment, providing network isolation for processes. Each namespace is like a copy of the network stack, including network interfaces, IP addresses, routing tables, and firewall rules. Network namespace are the first component that builds container networking, allow containers to have separate network stack. Second is virtual network devices. Network devices in Linux can be virtualized using technology such as like VET pairs, bridges, and tunnels. And in a nutshell, VET pairs or virtual Ethernet pairs are like the virtual Ethernet cables used to connect network namespaces to each other or to the host network stack. Bridges are like the virtual network switches used to connect multiple network namespaces and create a network segment. Tunnel are virtual network connections used to create overlay networks. The third is the overlay network. Overlay network are virtual network that routed on top of the underlying physical network infrastructure, often supported by software. Overlay network address the limitation of physical networks such as device dependency, location, and configuration complexity by providing one or more dynamic, secure, logical networks on the same physical network infrastructure. Overlay networks are often used to build the network of cloud platforms as well as used in Kubernetes. In Kubernetes, pod represents the smallest deployable unit. A pod consists of one or more containers that share a common network and stored resource. And to allow pods in the same cluster to exchange information with each other when designing the network for Kubernetes, the deployment team has proposed the following model. First, pods have IP address. The second, pods on node can communicate with all pods on all nodes without NAT. And third, agents on the node, such as system daemons, kubelet, can communicate with all pods on that node to serve health checks and monitoring. Kubernetes does not directly provide network solution, but defines a standard interface called Container Network Interface or CNI that third parties can implement and provide different network solutions for the Kubernetes. In addition to providing network connectivity for Kubernetes, CNI plugins can also support other features such as IPAM, network policy, observability, or some popular CNI plugins today are Calico, Flannel, Weave, Cilium, um, and a CNI plugin usually implement network for Kubernetes by creating an overlay network. The mechanism is usually to encapsulate packets with additional headers and route them through the cluster underlay network. Overlay networks can operate at layer 2, such as using the VXLAN protocol, or layer 3 using the IP in IP protocol. This process allows pods in the same cluster to communicate with each other as if on the same network. In overlay network using VXLAN, uh, VXLAN or virtual extensible LAN is a network virtualization technology that encapsulates Ethernet frame into UDP packets, creating an overlay network between nodes in the cluster. When pod send a packet to pod in another node, the packet will pass through the VTAP or VXLAN tunnel endpoint on the source node, be encapsulated with VXLAN header, and then further encapsulated into UDP packet and routed to the cluster underlay network to the VTAP on the destination node. The VTAP of the destination node then decapsulates the packet and forwards the packet to the destination port. In a overlay network using IP and IP, uh, the IP and IP protocol creates a tunnel between nodes in a cluster by encapsulate IP packets into another IP packet. When pod sends a packet into the pod on another node, the IP packet will pass to the tunneling endpoint of the source node, be encapsulated with an additional IP header, then routed to the cluster underlay network to the tunneling endpoint of the destination node. The tunneling endpoint of the destination node then encapsulate the packet and forward to the packet to the destination pod. In Kubernetes, pods are ephemeral, meaning they can be created and deleted at any time. Therefore, using IP address to communicate between pods is not a good option. Instead, Kubernetes you build in DNS service to resolve domain names to IP address. And core DNS is the default DNS server used in Kubernetes, usually deployed as a deployment with multiple replicas to ensure high availability and fault tolerance. Uh, as we discussed in previous section, connecting directly to pods via the pod IP address is not a good solution. Instead, Kubernetes provide an abstraction layer called services to provide a stable and reliable way to connect to pods. And there are several kind of service in Kubernetes. There are cluster IP, node port, load balancer, external name, and headless. And they kind of similar to each other, but with a small differences. And to provide load balancing for services, Kubernetes use kubeproxy, an agent running on each node in the cluster. It updates changes from the Kubernetes API server and configures the corresponding network rules. It has three modes. The first mode is the user space that is deprecated, and the two other modes are IP tables that kubeproxy use IP tables rules to route traffic to backend ports, and IPVS kubeproxy use the IP virtual server module to provide load balancing for services. And in IP table mode, when a service is created, kubeproxy will update the IP table rule on each node to reflect the current state of the service in the cluster. IP table rules are used to redirect traffic to backend pods based on the service cluster IP. Um, especially specifically in NAT table, kubeproxy will create kube service chain and kube SVC subchain corresponding to each service. In IPVS mode, when a service is created, kubeproxy will update the IPVS configuration on each node to reflect the current state of the service in the cluster. Okay, so some common issues with communication between pods may include pod cannot communicate with another pod. Packets may be dropped by firewall rules, network policy, or security groups. So we need to rely on the path of the packet to identify the issues. Then recheck the network policy, firewall rules, and routing table to identify and resolve the issues. And second, pod cannot communicate with servers. Pod may not be able to communicate with services due to errors in DNS resolution, load balancing, or connection issues. To resolve these issues, first we need to use DNS analysis tools to check DNS resolution. Then, based on the result, to segment and use packet capture to identify and resolve the error. An important note that the subnet of the pod and the service and the nodes in the cluster must not overlap with each other to avoid routing issues. And the third issue is agents on node cannot communicate with pods on that node. agent on node. The node may not be able to communicate with the pod due to routing errors or packet being dropped by firewall rules or network policy. This affects the monitoring health check process of the pod, making the pod in an unready state and unable to receive traffic. To resolve the issue, we need to use packet analysis tools to identify the issue, then check and update the file rules or network policy if necessary. Um, some common issues with DNS resolution may include the DNS pod failure. If DNS pod are not working or have issue, the DNS resolution process will fail and affecting service discovery and communication between pods and services. And to resolve this issue, we need to check the status of the DNS pods, logs, and DNS configuration to identify the error and fix it. The communication issues, um, pod may not be able to communicate with the DNS service. This also lead to DNS resolution failures. Um, and third is misconfiguration of the application domain name. And the fourth is DNS pod scaling. When resources of or the number of DNS pods are not sufficient to handle DNS request traffic, the DNS resolution process may be slow or fail. Um, and some common issues with load balancing in Kubernetes include the service endpoint misconfiguration, incorrect service configuration, missing endpoints, or incorrect endpoints can also cause load balancing issues, affect the service. And to resolve these issues, we need to check the service and endpoint configuration. Connection issues, pods cannot connect to the service or the connection is intermittent due to connection issue from the pod to the backend pods. Uh, to resolve it, we apply the techniques present previous. The third is kube proxy mode limitations. Because IP tables has some performance and scalability limitation. When the number of service and pod is large, it can cause latency and performance issues. To resolve these issues, we should consider using IPVS mode, uh, IPVS mode for kube proxy to improve. And the fourth is not configuring readiness probe. If the pods do not provide a readiness probe or readiness probe does not work correctly, kube-proxy may route the traffic to backend pods that are not ready, causing load balancing issues and reduce the reliability of the service. So to resolve this issue, we need to check and configure readiness probe for the pods and to ensure that kube-proxy only route the traffic to ready backend pods. Uh, so when encountering issues with Kubernetes networking, uh, so I have some basic step. Uh, First is master the basic of Kubernetes networking, understand concept and mechanism of Kubernetes networking, and the second step is check for the status and configuration of the related resources. The third step is checking the NS resolution. The fourth is checking network connectivity. And the fifth is always consider network policy and check if network policy and their network policy or file rules to ensure that traffic is allowed between pods and service and nodes. The sixth is analyze network traffic. to capture and analyze network packets using TCP dump or T-Shark to diagnose network issues. The seventh, we may need to collaborate and seek support from other teams. The eighth, we implement changes and verify the result. And the last step is document the step for references in the future. And we armed with some basic tools to debug Kubernetes networking. Uh, they are kubectl, CRI-CTL, NS enter for enter network namespace, IP link and IP route to check network interface and routing table, NS lookup and dits to analyze DNS resolution, ping and trace route to check network reachability, TCP dump and T-Shark to capture and analyze network packets, NetStat and SS to analyze network connection on node, IP tables and IPVS ADM to manage file rules and IPVS configuration. Oh, and I have prepared a small demo for to show you how to debug a Kubernetes faulty Kubernetes cluster using the technique present in the previous section. So the scenario here is that the front end applicant spot cannot call the backend API of an internal service. Log show that the front end applications are timing out when calling backend API service. So first we will check the status and logs of the pod. It seems that the backend, the pod of the front end and backend service are running normally. No error are found in the logs except the timeout issues. Then we verify the service endpoint. The service endpoint configuration is correct and has sufficient endpoint. Then the third step, we will check the DNS resolution. As you see, DNS resolution failed for the domain name of the service, and there may be an issue with the DNS service. And then I check for network policy, but there are no network policy applied, so traffic should be allowed between pods and services. Then I check the status of the DNS pod. The DNS pod are restarting frequently, indicate that an issue with the DNS service. So I check the deployment. So DNS deployment have resource constraint that has exceed memory limit, causing the frequent restart. And I update the deployment, then the problem is resolved. But we still have timeout log in the front end pod. So I check for network connectivity, and we can, as you can see, the connectivity to a pod on worker one is have some problem, and there are connectivity problem to worker one, and I start troubleshoot the connectivity between pod to pod and node to node. I use NS enter to enter the namespace of the front end pod, and use curl to send traffic, send a request to the backend service. Then I will capture the packet, use TCP dump to capture the packet on the worker 3 and worker 1. Then as you can see, the packet did reach the switch, that is CNI 0. That is the switch, and the packet reached the VXLAN terminal endpoint flanel1, and as you can see, the packet did leave worker 2. Uh, then I will capture the packet on the worker 1. As you can see, the packet did reach worker 1, and then I will capture the packet on CNI 0. But on CNI 0, we cannot uh, capture any packet, so the packet did not reach the suite, the virtual suite, that is CNI 0. Uh, so there may be dropped by the IP table, and I check the IP table configuration, uh, and you can see the IP table drop the UDP packet to port 8472, used by the Flanel C9 plugin. I remove the drop rule, and you can see we have restored the connectivity, and I will check again the to call some request, and connectivity seems okay now, and there is no timeout log in the front end part. Uh, so to summarize the content of my presentation, we have learned about the importance of Kubernetes networking in the operation of the Kubernetes cluster. The basic concepts of Kubernetes networking include container networking, CNI plugins, overlay network, and the Kubernetes networking model. Specifically understand how Kubernetes networking works, including how to create an overlay network, how pods communicate with each other, how DNS resolution works, and the load balancing mechanism. And I have provided a specific debugging method and a technique to identify and resolve common issue with Kubernetes networking. And thank you to participating and pay attention. If you have any question, please feel free to ask.
Okay, there is one questions on YouTube channel. Yeah, YouTube chat, and I will talk to you. Yeah, are you using physical server or virtual machine? Any specific problems with physical or virtual machine?
Sorry, can you repeat the
Uh,
question?
are you using physical server or VM
I
or
in the demo
no, no, yeah, in
I
the
use a, VM, virtual machine,
uh
but
oh
the method and the method I can see it is the same.
not specific problem. Oh, sorry. He he want in the production, not a demo.
In production,
In the
you mean
production.
the 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 the, the first incident that I have mentioned in the beginning?
Yeah.
Oh, we use VM. We use an OpenStack VM, to be precise.